Hello everyone, and welcome. Today we'll be exploring the fascinating world of discrete probability distributions. I'm excited to guide you through this topic. On this first slide, you'll see the title M18 Discrete Probability Distributions, brought to you by the Institute of Management Sciences, also known as JVK. In this presentation, we'll cover the fundamental concepts, key distributions, and their applications. So let's get started and discover what makes discrete probability distributions so important in management sciences. Let's take a closer look at discrete probability distributions. On this slide, you'll see a simple number line from 0 to 4, representing possible values of a random variable. In the context of probability, these are the different outcomes that can occur in a discrete setting. When we talk about random variables, we're referring to variables that take on specific values based on chance. Discrete probability distributions describe how likely each of these outcomes is. They are fundamental because they help us understand the probability structure of various phenomena. Next, we'll explore some key concepts related to these distributions, starting with the expected value, which essentially gives us the average or long-term average outcome of a random variable. Along with that, we consider variance, which tells us how spread out those outcomes are around the expected value. We'll also delve into specific types of distributions, starting with the binomial distribution. This distribution models the number of successes in a fixed number of independent trials, each with the same probability of success. It's very useful for scenarios like flipping a coin multiple times. We'll briefly mention the Poisson distribution, which is useful for modeling the number of events happening in a fixed interval or space, but we won't go into depth here. Similarly, there's the hypergeometric distribution, which applies when sampling without replacement, but we'll set that aside for now. Throughout this presentation, understanding these distributions and their properties will help us analyze real-world problems involving chance and uncertainty more effectively. Let's talk about random variables. A random variable is essentially a way to assign a numerical value to the outcome of an experiment. It helps us quantify what happens in a random process. Now, there are two main types of random variables to keep in mind. First, we have discrete random variables. These can take on a countable number of values, like 0, 1, 2, or even infinitely many, but still countable. Think of the number of cars passing through an intersection in an hour. It's countable, either a finite number or countably infinite. On the other hand, continuous random variables can take on any value within a certain interval or collection of intervals. For example, measuring the temperature of a room or the time it takes to run a race. These can be any value within a range, even incredibly precise ones. Understanding these distinctions is key, because it shapes how we analyze and interpret data in our overall study of probability and statistics. Let's look at an example with JSL appliances. Here, we're dealing with a discrete random variable that has a finite number of possible values. Specifically, imagine as the number of TVs sold at the store in one day. Now, this variable can only take on certain values, namely 0, 1, 2, 3, or 4. The key idea here is that because we're talking about a count of items sold in a day, the number of possible outcomes is limited and countable. This kind of variable is called a discrete random variable, and understanding its possible values helps us analyze and model real-world situations like sales data more effectively. Let's look at an example, JSL appliances. Here, we're dealing with what we call a discrete random variable. This means it can take on a sequence of values, and in this case, it's infinite. Now, imagine represents the number of customers arriving in one day. The key point is that can be 0, 1, 2, and so on. There's no highest number. We can easily count how many customers arrive each day, but there's no finite limit on how many could arrive. This is an important concept because it highlights how some random variables can have an unlimited range of possible outcomes, which we need to understand for modeling and analysis. Let's take a closer look at what random variables are and how we classify them. A random variable is basically a variable that takes on different values based on some random process or experiment. For example, consider the number of dependents you report on your tax return. That's a random variable because it can vary from person to person. We call this a discrete variable because it takes on specific, countable values. Next, think about the distance from your home to a store. This is a different kind of variable. It's measured in miles, and it can take on any value within a range. So, this is a continuous variable because it can take on infinitely many values within an interval. Finally, consider whether you own a dog or a cat. Here, the variable is categorical, with specific categories like owning no pets, only dogs, only cats, or both. Since these categories are distinct and separate, we call this a discrete variable as well. The key takeaway is that understanding whether a variable is discrete or continuous helps us determine the appropriate statistical methods to analyze it, which ties into the overall theme of how we handle different types of data in statistics. Let's talk about random variables. A random variable is essentially a quantity that comes from a random experiment, and because of chance, it can take on different values each time we perform the experiment. It's a way to assign numbers to outcomes, making it easier to analyze and interpret the results. For example, imagine tossing a coin 3 times. We can define a random variable, x, as the number of heads that appear in those 3 tosses. In this case, the possible values for x could be 0, 1, 2, or 3. Here, h represents a head, t represents a tail, and the value of x depends on how many h's we get in those tosses. This concept is fundamental because it helps us quantify uncertainty and variation in experiments, which ties directly into the overall theme of understanding variability and probability in our analysis. Let's look at the sample space for this experiment. The possible outcomes are TTT, TTH, THT, THH, HTT, HTH, HHT, and HHH. These represent all the different ways the 3 coin flips can turn out. Now, when we consider the possible values of x, which is the number of heads, it can be 0, 1, 2, or 3. For example, if all flips are tails, x equals 0. If all are heads, x equals 3. And for the other outcomes, x will be 1 or 2 accordingly. This association between outcomes and the number of heads is shown in the next slide, so keep that in mind. One key point here is that in this experiment, we have a total of 8 possible outcomes, since each flip has 2 options, heads or tails, and there are 3 flips. Because all these outcomes are equally likely, each one has a probability of 1/8 or 1/8. This equal likelihood is fundamental when calculating probabilities in such experiments, and it ties back to the broader theme of understanding how outcomes distribute in random processes. Let's take a closer look at this table. On the left, we have all the possible outcomes of flipping a coin 3 times. Each combination is represented by a sequence of HS and TS, heads and tails. For example, TTH means tails, tails, then heads. Moving across the top, you'll see the same sequences listed. Now notice the numbers on the right. These are the counts of how many times each sequence occurs in a sample space of 9 flips. For instance, the sequence HHT appears twice, and similarly, TTH appears once. The total at the bottom sums up to 9, which is the total number of flips we're analyzing. The key point here is understanding how these sequences distribute across multiple trials. This helps us see the probability of each outcome and illustrates the concept of sample space in probability. Recognizing the patterns, like how some sequences appear more frequently than others, is essential for grasping the fundamentals of probability distributions and randomness in experiments. Connecting this to the overall theme, this slide emphasizes the importance of understanding all possible outcomes and their frequencies. It's a building block for predicting probabilities and understanding the behavior of random processes in real-world scenarios. Let's take a closer look at the outcomes we observed in this experiment. The result of getting 0 heads occurred only once. That means, in our series of flips, we saw no heads just a single time. On the other hand, getting exactly 1 head happened 3 times. Similarly, flipping 2 heads also occurred 3 times. Interestingly, the outcome of getting 3 heads was quite rare, happening only once. Now, connecting this to our earlier discussion on random variables, we can see that these outcomes are tied to the value of the random variable, x by definition. X is a random variable because its values depend directly on the outcomes of the experiment. In this case, the values of x, how many heads we get, are determined by the results of each flip. This highlights a key point. The possible values of our random variable are not fixed beforehand. They are dictated by the actual outcomes we observe. This is fundamental to understanding how probability models work in experiments like this. Let's start by understanding what a probability distribution actually is. Essentially, it's a complete listing of all the possible outcomes of an experiment, along with their associated probabilities. This helps us see the likelihood of each outcome occurring. For example, in the case of tossing a coin 3 times, the experiment involves flipping the coin 3 times and counting the number of heads. The probability distribution in this context shows us all the possible numbers of heads we can get, like 0, 1, 2, or 3 heads, and how likely each of those outcomes is. Highlighting this is important because it provides a clear picture of the experiment's possible results and their chances. It's a fundamental concept that connects to the overall theme of understanding randomness and predicting outcomes in probability. So, when we talk about probability distributions, we're really mapping out the full landscape of what could happen and how often we can expect each result. Let's take a look at the probability distribution for 3 tosses of a coin. When we talk about these types of experiments, we're interested in understanding the likelihood of different outcomes. For example, the number of heads that can appear in 3 tosses. This distribution helps us see the probabilities of getting 0 heads, 1 head, 2 heads, or 3 heads. It's a great way to visualize how the possible outcomes are spread out and how their probabilities relate to each other. This connects to our overall theme of understanding randomness and how probability models help us predict and analyze these kinds of experiments more systematically. Let's talk about data types. Data types are fundamental because they define what kind of data we can store and work with in our programs. They help us organize and interpret data correctly. For example, there are basic data types like integers, which are whole numbers, and floats, which are decimal numbers. Then we have strings, which are sequences of characters, perfect for text data. Boolean types are also important, representing true or false values. Understanding these different data types is crucial because choosing the right one impacts how efficiently our code runs and how accurately it handles information. As we move forward, keep in mind that selecting the correct data type is a key step in designing effective and reliable software. Let's take a look at some examples of discrete random variables. As you can see, these are variables that can take on specific, separate values, often counts or categories. For instance, the number of cars passing through an intersection in an hour is a good example. It's a discrete variable because it can only be whole numbers like 0, 1, 2, and so on. Another example could be the number of students in a classroom. These are all situations where the variable takes on distinct values, unlike continuous variables, which can take any value within a range. Recognizing these examples helps us understand how discrete random variables are used in real-world scenarios and why they are important in probability and statistics. Let's talk about discrete probability distributions. Essentially, this is about understanding how the probabilities are spread out over the possible values of a random variable. In other words, it shows us how likely each outcome is. We can describe these distributions in different ways, using a table, a graph, or even an equation. Each method helps us see the probabilities clearly and understand the behavior of the random variable. This is a fundamental concept because it gives us a complete picture of the chances associated with different outcomes, which ties back to our overall goal of understanding uncertainty and variability in data. Let's talk about discrete probability distributions. The core idea here is that the probability distribution is described by what's called a probability function, which we denote as f(x). This function essentially gives us the probability for each possible value that our random variable can take. It's like a map showing the likelihood of every outcome. Now, for this function to be valid, it has to meet certain conditions. First, each probability fx must be greater than 0. That means no impossible or negative probabilities. Second, if we sum up all these probabilities across all possible values, the total must equal 1. This makes sense because the total probability of all outcomes in a probability space is always 100%. Similarly, when we talk about px, the probability associated with the random variable x, it must be non-negative, so px greater or equal to 0. And again, when we add up all these probabilities across all possible values, the sum should be 1. These conditions ensure that our probability function behaves consistently and logically, aligning with the overall theme of understanding how probabilities are assigned to discrete outcomes. They form the foundation for analyzing and working with discrete distributions effectively. Let's take a closer look at this example. Here, we've developed a tabular representation of the probability distribution for TV sales. This table summarizes past data on TV sales, specifically the number of units sold across different days. On the left, we see the number of units sold, ranging from 0 up to 4, and on the right, the corresponding number of days these sales occurred. For example, 0 units were sold on 80 days, 1 unit on 50 days, and so forth. At the bottom, the total number of days recorded is 200, which helps us calculate the probabilities. For each sales figure, the probability is simply the number of days with that sales amount divided by the total days. So, for 0 units, the probability is 80 divided by 200, which gives us 0.4. Similarly, for 1 unit, it's 50 divided by 200, resulting in 0.25, and so on. Notice that these probabilities add up to 1, confirming that this is a complete probability distribution. This table is important because it allows us to understand the likelihood of different sales outcomes based on historical data, which is essential for making informed predictions and decisions in our overall analysis. Now, let's take a look at discrete probability distributions. On this slide, you can see the probabilities associated with different values of our random variable, which in this case is TV sales. The values range from 0 to 4, representing the number of TVs sold. Each value has a corresponding probability: 0.1 for 0 TVs sold, 0.2 for 1 TV sold, 0.3 for 2 TVs, 0.4 for 3, and 0.5 for 4. This graphical representation helps us visualize how likely each sales figure is. Notice how the height of each bar indicates the probability of that specific outcome. The key idea here is that, in a discrete probability distribution, each possible outcome has a probability that sums up to 1 across all outcomes. Understanding this distribution allows us to analyze the likelihood of different sales scenarios, which is crucial for making informed business decisions. It's a fundamental concept in probability that helps us model real-world situations where outcomes are countable and discrete. Let's talk about discrete probability distributions. As we mentioned earlier, the probability distribution of a discrete random variable can be represented in different ways, such as a table, a graph, or a formula, that show the probability associated with each possible value the variable can take. In this example, we're looking at the number of radios sold at Sound City in a week. The variable x represents the number of radios sold, and the probabilities p, x, give us the likelihood of each outcome. For instance, the probability that no radios are sold equals 0 is 0.03, which is quite low. Selling 1 radio has a probability of 0.2, or 20%. The most common scenario is selling 2 radios, with a probability of 0.5, or 50%. Selling 3 radios has a probability of 0.2, and 4 radios is even less likely at 0.05. Finally, the chance of selling 5 radios is only 0.02. The key takeaway here is that these probabilities sum up to 1, ensuring we account for all possible outcomes. This table helps us understand the likelihood of different sales levels, which is useful for planning and decision-making. Overall, this example illustrates how discrete probability distributions give us a clear picture of the possible outcomes and their chances. tying back to our overall goal of understanding randomness and variability in real-world situations. All right, let's talk about the expected value of a discrete random variable. Essentially, this is the average or mean value we anticipate based on the probabilities of different outcomes. It's a key concept because it gives us a single number that represents the center of the distribution. Now, in this example, we're looking at the expected number of radios sold in a week. We've listed possible sales numbers, from 0 up to 5 radios, along with their associated probabilities. For instance, the probability that no radios are sold is 0.03, and the probability that one radio is sold is 0.2. To find the expected value, we multiply each possible outcome by its probability. So for 0 radios, we have 0 times 0.03, which equals 0. For one radio, it's 1 times 0.2, giving us 0.2. We do this for each outcome and then sum all these products. Adding them up, the total expected value of radios sold per week is 2.1. This means, on average, we expect about 2.1 radios to be sold each week, based on this probability distribution. The key takeaway here is that the expected value is a weighted average, where outcomes with higher probabilities influence the mean more. It's a useful measure because it helps us understand what we can typically expect in uncertain situations, and it connects directly to the overall theme of understanding and predicting variability in data. Today, we're diving into the concepts of variance and standard deviation, which are essential measures in understanding the variability of a discrete random variable. The variance essentially tells us how spread out the values are around the mean. When we talk about the variance of a discrete random variable, we're referring to the average of the squared deviations from the mean, weighted by their probabilities. It's a key indicator of the dispersion in our data. Now, the standard deviation is simply the square root of the variance, which brings us back to the original units of measurement. This makes it easier to interpret, since it's in the same unit as the data itself. These concepts are fundamental because they help us quantify the uncertainty and variability in probabilistic models, tying directly into our overall theme of understanding randomness and variability in data. Let's take a closer look at variance and standard deviation through this example involving the number of radios sold in a week. On the left, we have the number of radios, labeled as X, and on the right, the corresponding probabilities, P, X. Notice that the probabilities sum up to 1, which confirms that we're working with a proper probability distribution. To understand the variability in this data, we calculate the deviation of each value from the mean, which here is 2.1 radios, and then square those deviations. For example, when 0 radios are sold, we subtract the mean, 2.1, from 0, giving us minus 2.1. Squaring that gives us 4.41, and multiplying by the probability of 0.03 gives us 0.1323. We repeat this process for each value of X, multiplying the squared deviation by its probability. Adding up all these products results in what we call the variance, which in this case is approximately 0.89. Variance essentially measures the average squared deviation from the mean, giving us a sense of how spread out our data is. The standard deviation, which we haven't explicitly calculated here, but is simply the square root of the variance, provides a more interpretable measure of spread in the original units, in this case, radios. So, understanding variance and standard deviation helps us quantify the variability in our data, which is crucial for making informed decisions and understanding the overall behavior of the data set. Let's take a closer look at the expected value and variance, summarized here. The expected value, or mean, of a random variable is essentially a measure of its central location. It gives us an idea of where the center of the distribution lies. Think of it as the average outcome we would expect if we could repeat an experiment many times. On the other hand, the variance tells us how much the values of a random variable tend to vary or spread out around that mean. A higher variance indicates more variability, while a lower variance suggests the values are more tightly clustered. Now, the standard deviation, represented by the Greek letter sigma, is just the positive square root of the variance. It's often more intuitive because it's expressed in the same units as the original data, making it easier to interpret. Mathematically, the variance is the sum of the squared deviations from the mean, weighted by their probabilities, written as var. X equals sigma squared. And the expected value is the sum of each value times its probability, represented as Ex equals mu. Understanding these concepts helps us grasp the overall behavior of a random variable, where it tends to center and how spread out its possible values are, linking directly to the theme of analyzing uncertainty and variability in data. Let's now turn our attention to discrete probability distribution models. This is a fundamental concept because it helps us understand how probabilities are assigned to different possible outcomes in situations where the outcomes are countable or discrete. For example, think about rolling a die or flipping a coin. Each possible result has a certain probability, and these probabilities sum up to 1. Understanding these models is key because they form the basis for analyzing many real-world problems involving discrete data. They allow us to predict the likelihood of various outcomes and make informed decisions based on those predictions. Throughout this section, we'll explore different types of discrete distributions and how they apply in different contexts. Recognizing these models helps us see the bigger picture of probability theory and its practical applications in areas like quality control, risk assessment, and decision-making. So, as we go along, keep in mind that these models are the tools that help us quantify uncertainty in discrete scenarios. Let's take a closer look at the 4 key properties of a binomial experiment. First, the probability of success, which we denote as P, does not change from trial to trial. This means that each time we run the experiment, the chance of success stays constant, making the process predictable in that sense. Second, the trials are independent. This is really important because the outcome of one trial doesn't influence or affect the outcome of the next. Each trial stands alone, which simplifies our calculations and understanding. Third, on each trial, there are only 2 possible outcomes: success or failure. This dichotomy is what makes it a binomial situation, nothing in between. Finally, the experiment consists of a sequence of n identical trials. These trials are repeated under the same conditions, which allows us to analyze the results collectively and apply binomial probability formulas. Putting all these properties together helps us understand why the binomial distribution is such a powerful tool for modeling situations involving repeated, independent trials with 2 possible outcomes. Today, we're focusing on the binomial distribution, which is all about understanding the number of successes we can expect in a fixed number of trials. The key idea here is that we're interested in how many times a specific event occurs, successes, in a set of n trials. We use the variable to represent the actual number of successes that occur in those n trials. So, when we talk about the binomial distribution, we're essentially looking at the probability of getting x successes out of n, given certain conditions like the probability of success in a single trial. This concept ties into the overall theme of probability distributions, helping us model real-world scenarios where outcomes are binary, success or failure, and we want to understand the likelihood of different outcomes. Let's take a closer look at the binomial distribution. Here, you'll notice that f, x, represents the probability of getting exactly x successes in n trials. Think of it as a way to find out how likely a specific number of successes is when you're running a series of experiments or trials. Now, n is simply the total number of trials you're conducting, like flipping a coin 10 times, for example. And p is the probability of success on any one trial, so if you're flipping a fair coin, p would be 0.5. This setup helps us understand the chances of different outcomes in situations where each trial is independent, and the probability stays the same each time. The binomial probability function is a key formula here, which allows us to calculate those probabilities precisely. Overall, this concept is fundamental because it connects the probability of individual events to the overall distribution of outcomes across multiple trials. It's a powerful tool for understanding real-world problems involving success and failure in repeated experiments. Now, let's take a closer look at the binomial distribution, specifically the binomial probability function. This function helps us understand the probability of a particular sequence of trial outcomes. Imagine you have n trials, and you're interested in the probability of getting exactly x successes. The binomial probability function calculates the likelihood of that exact scenario occurring. Think of it as counting all the different ways you can achieve successes out of n trials, each with its own probability. In essence, it gives us the number of experimental outcomes that result in exactly x successes. This is a fundamental concept because it allows us to predict the chances of specific outcomes in situations where there are fixed numbers of independent trials, each with the same probability of success. Connecting this to the broader theme, understanding the binomial distribution enables us to analyze real-world problems more effectively, whether we're dealing with quality control, medical testing, or any scenario involving repeated, independent events. All right, let's dive into this thinking challenge. Imagine you're a telemarketer selling service contracts for Macy. You've sold 20 out of 100 calls, so your probability of success on any given call is 0.2. Now, if you make 12 calls tonight, what are the chances of different outcomes? First, what's the probability of no sales at all? That's when all 12 calls result in no sale. Then, what about exactly 2 sales? And at most 2 sales, that means 0, 1, or 2. Finally, at least 2 sales, that's 2 or more. These questions are great because they help us understand how probability works in real-world scenarios, especially with binomial distributions, where each call is an independent event with the same chance of success. By analyzing these probabilities, we can better manage expectations and strategize for different outcomes. It's a perfect example of applying probability theory to everyday decision-making, connecting the math to actual business situations. Let's take a look at some solutions to our problem. First, the probability that 0 events occur, p0, is quite low, indicating that it's unlikely nothing happens in this scenario. Next, the probability of exactly 2 events happening, p2, is 0.2835, which is significantly higher, suggesting that 2 events are fairly common. Now, if we want to find the probability of at most 2 events, that is, 0, 1, or 2 events, we add those individual probabilities together. So p, at most 2 equals p0 plus p1 plus p2, which sums up to 0.0687 plus 0.2062 plus 0.2835, giving us a total of 0.5584. This means there's about a 55.84% chance that we'll see 2 or fewer events. On the other hand, if we're interested in the probability of at least 2 events, that is, 2 or more, we can think of it as 1 minus the probability of fewer than 2 events, which is just 0 or 1 event. So p, at least 2, equals 1 minus the sum of p0 and p1. Substituting the values, that's 1 minus 0.2062, resulting in 0.7251. This tells us there's a 72.51% chance that 2 or more events will occur. These calculations are crucial because they help us understand the likelihood of different scenarios, which connects directly to our overall goal of assessing risk and planning accordingly. Let's take a closer look at this thinking challenge. The Department of Labor Statistics reports that, in Treble County, about 2% of the workforce is unemployed. Now, if we take a random sample of 15 workers from the county, we're interested in calculating some probabilities using the binomial distribution. First, we want to find the probability that exactly 3 of these workers are unemployed. Based on the binomial table, this probability is approximately 0.0029. That's quite a small chance, which makes sense because with only a 2% unemployment rate, seeing 3 unemployed workers out of 15 is relatively rare. Next, we consider the probability that 3 or more workers are unemployed. To find this, we subtract the probabilities of having 0, 1, or 2 unemployed workers from 1. The sum of those probabilities, 0, 7,386, 0.2261, and 0.0323 adds up to about 0.997. So subtracting that from 1 gives us approximately 0.0031. This part of the problem highlights how we can use the binomial distribution to assess the likelihood of different outcomes in a small sample, especially when dealing with probabilities like unemployment rates. It ties back to the overall theme of understanding variability and probability in real-world data. So in this slide, we're looking at the probability that at least one of the sampled workers is unemployed. The key point here is that the probability of having 0 unemployed workers is 0.7386. Therefore, the probability of having at least one unemployed worker is simply 1 minus that, which gives us 0.2614. This makes sense because if the chance of 0 unemployed workers is about 73.86%, then the chance that there is at least one unemployed worker is roughly 26.14%. Next, we consider the probability that at most 2 workers are unemployed. By summing the probabilities for 0, 1, and 2 unemployed workers, which are 0.7386, 0.2261, and 0.0323 respectively, we get a total probability of about 0.997. This high probability indicates that it's very unlikely to have more than 2 unemployed workers in the sample. Overall, this slide highlights how we can use probability to understand and quantify unemployment patterns within a sample, which connects to our broader theme of analyzing workforce data and making informed inferences based on sample results. Let's look at this example. Imagine a city engineer who claims that half of the bridges in the county, so 50%, need repair. Now, suppose we randomly select 10 bridges from the county. The question is, what's the probability that exactly 6 of those bridges need repair? This situation fits the binomial distribution criteria because we have a fixed number of trials, 10 bridges, and each trial has only 2 possible outcomes: needs repair or doesn't need repair. Also, the probability remains constant at 0.5 for each bridge, and the trials are independent. So, when we verify the calculations, we find that n equals 10, p equals 0.5, and the probability that exactly 6 bridges need repair is approximately 0.2051. This example illustrates how binomial probabilities help us understand the likelihood of a specific number of successes, in this case, bridges needing repair, in a fixed number of independent trials. It ties back to our overall theme of understanding binomial situations and calculating precise probabilities. So let's talk about the probability that 7 or fewer bridges need repair. Essentially, we're trying to find p of x less than or equal to 7. We can do this by summing up the probabilities for all values from 0 up to 7. That means adding p of x equals 0, p of x equals 1, and so on, all the way to p of x equals 7. In our calculations, this sum comes out to approximately 0.9454. Another way to look at this is to use the complement rule, which can sometimes be easier. Instead of summing all those probabilities directly, we can subtract the probability that more than 7 bridges need repair. That is, the probabilities for x equals 8, 9, and 10 from 1. When we do that, we find that p of x less than or equal to 7 is also about 0.9454. The key takeaway here is that there's a very high likelihood, around 94.5%, that 7 or fewer bridges will need repair. This kind of probability helps us understand the overall risk and plan accordingly, fitting into the broader theme of assessing and managing infrastructure reliability. Let's take a look at this example from Evans Electronics. Wendy, who manages the company, is quite concerned about employee retention. Over the past few years, they've been seeing a turnover rate of about 10% each year among their hourly workers. To put that into perspective, if you pick any hourly employee at random, there's roughly a 10% chance they won't be with the company next year. This kind of probability helps us understand and quantify the risk of losing employees, which is crucial for planning and improving retention strategies. It ties back to our overall theme of using probability to make informed business decisions. All right, so in this example, we're looking at selecting 3 hourly employees at random. The big question is, what's the probability that exactly one of them will leave the company this year? To figure this out, we'll use a specific equation from earlier in the presentation. Let's define our key variables. First, P equals 0.10, which means each employee has a 10% chance of leaving within the year. Next, N is 3, because we're choosing 3 employees, and is 1, since we're interested in the scenario where exactly 1 employee leaves. By plugging these numbers into our probability formula, we can calculate the likelihood of that specific outcome. This example is a good way to see how probability models can help us make informed predictions about employee turnover, which ties back to our overall theme of understanding and managing workforce risks. All right, let's take a closer look at this tree diagram. Here, we're tracking the possible outcomes as each worker makes a decision. Starting with the first worker, there's a probability of staying with the current task, which is about 90%, and a smaller chance, around 10%, that they leave. The second and third workers have similar decision points, with the same probabilities for staying or leaving. Now, as we follow the branches of this tree, notice how these probabilities multiply. For example, if all 3 workers decide to stay, the probability is quite high. Specifically, 0.9 raised to the third power, which is about 0.729. This is represented in the diagram by the larger leaf, indicating that staying with the task through all 3 workers is the most likely outcome. On the other hand, if any worker leaves, the probabilities drop significantly, especially in scenarios where multiple workers leave. These smaller branches, or leaves, show the likelihoods of different sequences of staying or leaving. For instance, the smallest probability, about 0.001, is when all 3 decide to leave. This diagram helps us visualize the various potential paths and their associated probabilities. It's a great way to understand the overall chances of different outcomes happening, based on each worker's decision. Connecting this back to our broader theme, it highlights how small individual probabilities can compound, affecting the overall system behavior. Let's take a closer look at the binomial distribution, which is really useful when we're dealing with a fixed number of independent trials, each with the same probability of success. The expected value, or mean, of this distribution is given by the formula EX equals mu, which is simply n times p. This tells us what the average number of successes we can expect over many trials. Moving on to the variance, which measures how much the outcomes tend to spread out around that mean. The variance is calculated as np times 1 minus p. This part is important because it shows that the variability depends on both the number of trials and the probability of success. Understanding these 2 key points, the expected value and the variance, helps us grasp the overall behavior of the binomial distribution. The expected value gives us a central point, while the variance tells us about the spread or consistency of the results. Finally, the standard deviation, which is simply the square root of the variance, provides a more intuitive measure of how much individual outcomes are likely to deviate from the mean. These concepts are fundamental because they give us insight into the distribution's shape and variability, which are essential when analyzing binomial data in real-world scenarios. Let's take a closer look at Evan's concern about employee retention. Recently, management has observed that about 10% of hourly employees leave the company each year. This means that if we pick an hourly employee at random, there's a 0.1 probability that they won't be with us next year. Now, suppose we select 3 hourly employees at random. We're interested in finding out the probability that exactly one of these 3 will leave this year. To figure this out, we need to understand some key concepts from probability theory, specifically the binomial distribution. The binomial distribution helps us model the number of successes, in this case, employees leaving, out of a fixed number of trials, which is 3 here. The probability of exactly 1 employee leaving can be calculated using the binomial formula, considering the probability of 1 success and 2 failures. In addition to that, we can also determine some summary measures. The mean, which tells us the expected number of employees leaving, the variance, which measures how much the number of departures might fluctuate, and the standard deviation, which is simply the square root of the variance, giving us a sense of the typical deviation from the mean. These calculations are not just numbers. They help us understand the overall trend and variability in employee turnover, which is crucial for planning and improving our retention strategies. So, by analyzing these probabilities and statistical measures, we gain valuable insights into managing our workforce more effectively. Now, let's look at the key statistical measures for this scenario. The expected value, denoted as E, X, or mu, is calculated as 3 times 0.1, which equals 0.3 employees. This tells us that, on average, we expect about 0.3 employees in this context. Moving on to the variance, written as var, x, or sigma squared, it's computed as 3 times 0.1 times 0.9, giving us 0.27. Variance gives us an idea of how much the number of employees might vary around that average. And finally, the standard deviation, which is the square root of the variance, helps us understand the typical deviation from the mean. It's important because it provides a sense of the variability or spread in our data. Overall, these measures, mean, variance, and standard deviation, are fundamental because they help us grasp the expected outcome and the variability around it in probabilistic terms.